It's afternoon, yeah. So welcome to IFAS, to the IFAS on AI and the Data Sciences Seminar Series organized by IFAS Faculty AI Working Group. My name is Golmar Golmohammadi. I'm an assistant professor in the Department of Soil, Water, and Ecosystem Sciences at University of Florida. I'm also a member of seminar committee, and today is my great pleasure to introduce our internal speaker, Dr. Joel Harley, who is an associate professor and a Kenton Linda-Fields faculty fellow in the Department of Electrical and Computer Engineering. He is also the director of the NSF Center for Big Learning. His academic background is in signal processing and artificial intelligence. His research interest integrates physical knowledge with machine learning to advance the fundamental sciences and engineering. Dr. Harley is a recipient of several awards, including 2021 Achenbach Medal from the International Workshop on Structural Health Monitoring, a 2020 IEEE Ultrasonics, Ferroelectrics, and Frequency Control Society Star Ambassador Award. He received a 2020 and 2018 Air Force Summer Faculty Fellowship, is 2017 Air Force Young Investigator Awards, and he received a 2014 Carnegie Mellon A.G. Jordan Award for academic excellence and exceptional services to the community. He has published more than 180 technical journal and conference papers, including 4 best student papers. He is also an associate editor and member of editorial board for Structural Health Monitoring and International Journal. He is a member of editorial board for Ultrasonics, a member of IEEE Ultrasonics, Ferroelectrics, and Frequency Control Society Technical Program Committee, and he is a member of the IEEE Signal Processing Society and a member of Acoustics Society of America. Today, Dr. Harley is going to present about integrating data-driven machine learning and knowledge-driven analysis for quantifying ecosystem services. Now, please join me to welcome Dr. Harley to the stage, and Dr. Harley, floor is yours. Please go ahead and share your screen. Yeah.
Wonderful, wonderful. Thank you very much for the introduction. So I'm going to have to start my presentation here after that introduction of probably clearly explaining myself, because you may hear the introduction and say, oh, who is this person? Why is he presenting at this seminar? He sounds nothing like someone who should be presenting at the seminar, which I would not blame you for thinking that. So let me start off briefly by talking a bit about myself, why I'm presenting here, what we're doing, and why you should be interested. So, as said, my name is Joel Harley. I'm an associate professor and Kenton Linda Fox Fellow in the Department of Electrical and Computer Engineering. All of my background is in electrical engineering, got my bachelor's degree at Tufts University in electrical engineering, went to Carnegie Mellon University for a master's degree and PhD in electrical and computer engineering. But what my research interests are really focus on the intersection of a whole variety of fields. So really it tends to be physics, or it can be more general knowledge, ecological knowledge, agricultural knowledge, for example. So physics and knowledge combined with machine learning and combined with signal processing. And signal processing already kind of fills a little bit of the void between machine learning and physics and knowledge, because I tend to think of the people who do signal processing are the people who care about data analytics, but also with a little bit of physics on the side. And as a short story, this all kind of started out with me as a graduate student. So I was in electrical and computer engineering doing sort of data sciencey things. It was before data science was really a term that existed all that much. But I worked mostly with civil engineers. And I learned a lot of how to work with other people. So my advisor was very much into, data analysis and build these statistical models and do all these other things. And then the civil engineers that I ended up working with on this project were very experimentalists, where they said, "Oh, don't trust any of those models. Those don't work. Just collect data and interpret the data. Don't use anything else." And so kind of my PhD upbringing got me very, very curious about the intersection of these kind of topics of I see both sides of the picture. I see we should be building models, using statistics, understanding things from a broad fundamental perspective, but at the same time, data is data, and data is much more complicated than oftentimes the pure modelers will give it granted for. So a lot of my work has kind of tried to walk this line of how do we approach it from both directions. And I started out with civil engineers doing work in this field of non-destructive evaluation and structural health monitoring, which is where a lot of my awards and stuff are from. So that's what I did as a PhD student. But as a faculty member, I have branched out, noticing that this is a problem not just in the field that I started in, but in a lot of other fields. So my broad view is, how do I try to solve these problems? And I've applied them to a whole variety of problems. Sort of my work starting from my PhD is all in this category of dealing with ultrasound and looking at data over long periods of time. I have a little bit with monitoring of electrical systems as well. And this is kind of getting into the newer work where I'm finding, oh, these problems exist in other places. So measuring ecosystem services and soil nitrogen monitoring recommendations is what I'm going to be talking about today. But also work going into material science, looking at biomedical engineering, and a little work with physics on the side. This is just a small seed grant. So this is just to kind of explain where I'm coming from, what I've done. I work with a lot of collaborators. I'm clearly not an expert in everything that I work in. My collaborators with IFAS here, well, I guess Alina is technically not an IFAS, but Alina's been working with IFAS for a long time. We have Jose and Lincoln and Zhang here in agronomy and horticultural sciences are my primary collaborators in this field. And then I'm sure a lot of you know Alina as well, because she has been working in this space far longer than I have. So let me talk to you then a little bit about the work that we've been doing. And I'll note this started with Alina. So she's the one who kind of got me involved. We're both in electrical and computer engineering. And she, I guess it was 3-4 years ago now, said, hey, we need more people who know AI and can do some of this stuff. You should join in and take part of it. So I decided, yeah, that makes sense. So it's been Alina and I working with Jose and Lincoln, and Chong is kind of the more recent member, and she's been invaluable to a lot of this. And this started as kind of we got a legislative budget request from the Florida legislature to look at how to evaluate ecosystem services across Florida. And specifically, we were interested in how do we quantify ecosystem services across Florida in hopes of later valuing what those ecosystem services are. So we started with a relatively large team of students that were crossed between both engineering and IFAS. And for me, this was really a huge learning opportunity. So this was a one-year project with a lot of students, and I spent a lot of time just trying to learn, particularly from the IFAS students, because I knew the engineering side, but the agriculture side, the ecology side was very new to me. So learning a lot from them and seeing where we could go and finding where gaps were within the field. So as I kind of stated, our goal here is, can we quantify ecosystem services? So all of these services that we get from the environment that are generally beneficial to society. Can we quantify how much is there? It doesn't necessarily have to be a physical unit, but some kind of metric some quantity of what this is. How do we deal with this is difficult, especially if we're talking about the scale of entirety of Florida. Ecosystem services and how we can relate them to things vary all across Florida. It's a very complex problem. So that actually makes it pretty natural for the use of artificial intelligence. We have a problem. We can potentially collect a lot of data, and I'll talk about that. The data is an issue to some degree, but we can collect data. Data is very complex, and we want to build some AI framework to untangle this complexity and build some way to quantify the ecosystem services. And as I said, there are some challenges with this. Some data can be acquired pretty readily. One of those, which we'll see a lot, is like satellite imagery. We have the capability to acquire satellite imagery. There are databases for certain things, like iNaturalist exists. It has lots of data all throughout the state of Florida, but it's still quite limited. It is very biased, which we'll see in certain regions. So overall, if we're talking of fairly large scope, data that we have is actually fairly limited, especially in places where there aren't many people. And then furthermore, truth labels. So when you're building in a AI system, a supervised AI system, I put in some kind of input and I need an output, and you need to train with the truth at some point. Truth labels is very, very, very difficult to find. So that's one of the challenges that we've had to overcome. And we decided the first round of going and trying to understand this was there are lots of different ecosystem services we can look at. And I should actually mention we'll be doing both biodiversity here and soil nutrients. Should highlight that one as well. But we started out this project with biodiversity, more or less because it's a little bit easier to quantify. Water quality and water quantity, for example, have a lot more dimensions to it. Biodiversity, while still pretty complicated, is a more simple concept to understand. We're also going to talk a little bit about soil nutrients in this presentation, and how we can obtain soil nutrients from our machine learning algorithms. And actually, I'm going to just skip to the next slide. So we collect our data from a variety of places. So the project started with us going out and collecting field data. So you can see actually all the students out in the field collecting data. This is both IFAS students and engineers. And I think the engineers were very surprised when we got them to go out into the field and basically figuring out what plants were out there. And most of them had never thought that's what they were going to do as part of their research. I think a lot of them got a lot out of it and learned a lot. So we collected field data. We've been busy gathering public map data. So one of the nice things about looking at these large areas, there is a lot of land use, soil surveys, topology data that can all be used for artificial intelligence purposes. We are collecting satellite imagery and remote sensing data. So we have an arrangement with Planet Labs, which is probably the largest player in satellite imagery right now, commercial satellite imagery at least. We're trying to collect basically a satellite image of Florida every month, of which we can then take that satellite imagery and produce maps of ecosystem services across the state. And we can do that with the SkySat, so 50-meter resolution, 5 bands, so it's multispectral. PlanetScope can give us much better resolution, but getting the entire state of Florida with PlanetScope would, one, be monetarily unfeasible, and also would require a huge amount of data with 3-meter resolution and 8 bands. But we have been using that to collect areas of which we are doing specific validation for specific ecosystem services. And then there's finally citizen science data out there, the big one for biodiversity being iNaturalist, which there's now millions of observations of species all across the state of Florida, and we can collect that. And we've also been busy collecting research grade data sets from various people within the communities who have been collecting data at various areas in Florida. I'll show some of that in the future. So this is the kind of data sets that we've been utilizing. In terms of doing the AI, I would say there's really 3 different routes that we're trying to take with this. The first kind of more traditional route for artificial intelligence and machine learning, I'm just calling the data route. And the data route is I have lots and lots and lots of data, and I can just throw that all into an AI framework and have some labels for that, and magically we can get some kind of quantification of ecosystem services. For the reasons I kind of described already, this tends to be very difficult for us to do. We often don't have the labels, we sometimes don't have much data, or we have very sparse data or imbalanced data. Certain areas of Florida have more data than others. So in many ways, the data route is a difficult route to go for these sorts of applications. And I think that's true in many, many fields, right? Most fields do not have an internet of text and images that we can just train from, like we have now with LLMs and things like that. So we have to figure out different ways to deal with these data issues. The 2 other routes that I'll be talking about is one where I call the knowledge route, where we have no longer a large measured data set, but a small one. So we have a little bit of information that we can use. Small is a relative word in this case, I should note, because it's still hundreds of gigabytes of data for satellite imagery. But what we incorporate into this is some sort of knowledge. In this case, it'll be ecological knowledge. It will be knowledge of land use for what I'll talk about. And we can incorporate it as actually land use and how land use relates to different ecosystem services. So we can incorporate this information into our AI framework to basically give it this expert knowledge, use it in a fairly indirect fashion, and make it work for us. And the last one I call is the synthetic data route, where we have a large simulated data set. So there are a number of, across many sciences, there are lots of different simulation engines. And this is one thing that I learned as a graduate student, that lots of simulation engines exist for all sorts of things, but generally when you compare your data with the simulated data, it doesn't quite match up enough. It may match up enough to say, yes, they're telling me the same thing, but if you actually want to do data science, data processing on it, they're usually nowhere close enough to do anything. It's more of a, I can visually look at the 2 and say, yes, they make sense, they agree with each other. No quantifiable way to really compare them in most cases. So the question here is, can we make these useful, right? From a quantitative perspective, oftentimes these simulation data sets are not that useful to us. But can we, by putting them into an artificial intelligence framework, and then also inputting a small amount of measured data and saying, okay, from my large data set as well as my small data set, can I learn something from that? The large data set basically giving me sort of the broad strokes of information, the small data set fine-tuning that information to get my ecosystem services. So I'm going to talk about each 3 of these, starting with the data route. In terms of the students or postdocs who have been working on this, this is 2 of the students that have been working on it. Alston had been working on really gathering lots and lots of the data and providing lots of advice to me on how this all works and what this means. Salil here has been working with the data and trying to develop algorithms to try and understand this. And the data we're working with in this case is all of the large public and research data sets that we've collected across the state of Florida for species, basically, and looking at biodiversity. So some of these, so there's the Global Biodiversity Information Facility, that includes all the iNaturalist data. And then we've been collecting data from various groups across Florida, NPS, FNL, the Orway Swisher Biological Station, University of Florida DeLuca Preserve. And our data set kind of looks like this when you look at it. So the green values are all of these public citizen science data sets all across the state. The yellow ones are our research data, so data collected by certain research groups across the state. And then there's a few others that are labeled that are much smaller. So I don't even think I can see where some of them are. If you look very carefully, you might be able to see it. But by and large, the citizen science data set is the strongest. But we can see some issues with it. For sure, they are definitely biased. Gainesville, right? Tampa area, everywhere along the coast. And then there are areas that there really is hardly any data that we can work with. So there's the concentrations in public locations, missing data, places just where there are no people. So we don't have people telling us where there are species. So this is just kind of preliminary results that I'll be showing, but it's almost going to just highlight the challenges of doing this. So we spent some time, we built a database of plant species, no D there. Created a grid. So basically we've created this big grid of satellite images. I guess we're not actually going to use the satellite images in this particular case. We're going to move into using satellite images next, but we have a grid that has been placed across the entirety of Florida, of which we have satellite images for each of these points. And then what we've been able to do is compute biodiversity scores across. And there's a lot of different biodiversity scores out there that people have seen. And this is just based on the data that we have. This is just the collection of data that has been provided. And the one that we're showing in this particular case is the Shannon index, which is a measure of entropy, more or less. I won't go more into that. We mostly chose this one because it appeared to be the least biased due to the number of species that we had in a particular grid location. That being said, if we overlap this with the locations of which we have collected data, you can see that that's still not very true. It seemed to be the least biased of all of the metrics that we used, but it is clearly still very biased. All of these red points indicate where our points are, and the green points, right? Higher the green points, the more biodiversity, basically, according to the Shannon index. So, well, more biodiversity still tends to be around these urban areas, which doesn't make sense in general. But that's because that's where most of our data is coming from. So we're working on incorporating the satellite imagery into this, which I think will address some of the challenges. But this is a nice demonstration that we can't just easily, at least, rely on pure data to help us, because the data is going to be very biased and is not going to help us find areas right here where we just don't see animals, or we don't have people reporting animals, I should say, or plants in this case. This is just plants. So we need other routes to take, unless we want to do a very systematic exploration of every single location in Florida, but that would require probably billions of dollars and lots of time, which I don't think we're going to be able to do. So that takes us to another route, and I'll call this one the knowledge route. And this is the team that's been working on this route. So two people from engineering, Tian and Austin. Austin just graduated with his master's, and Jack. And Jack's been the advisor on a lot of this and kind of directing ways to go and routes, and he's become kind of a fixture in my lab since he started working. Austin kind of built our entire database and pipeline for doing all the processing with the satellite imagery, and Tiana has really been responsible for building all the algorithms that I'm going to show here. So this knowledge route. So we're going to consider multispectral satellite imagery. So as I said, we're capable of collecting satellite imagery of all of Florida, basically every month, in a multispectral manner. You see here Alachua County, with Gainesville there in the middle. University of Florida is over here. I believe this is 13th, but that might be Waller Road. Downtown's in this area. So, and what we're going to do for our methodology is we're going to divide this map into superpixels. So superpixels basically based on similar spectral content. So 5 bands. Let's find regions that look similar and are in similar locations as well. and group those all together in what we'll call superpixels. So then those have their own values or statistical values, which I'll mention in a second. And there's a bunch of different algorithms for solving this. We use SNCC. If you're familiar with this field, SNCC is, I think, the more common algorithm. This is a little bit more of a robust version of SNCC. Then we compute spectral statistics for each of these superpixels. So rather than them having a single color value, or really 5 bands of color values, we compute things like the mean, median, max value amongst the pixels, or sorry, the spectral content and whatnot, and that becomes the values for each of these superpixels. And then we obtain land cover, or I should say land use labels. Oh no, land cover, excuse me, land cover labels. So we have land cover labels, which we can see here on the right-hand side for Alachua County. I don't remember what all of these are, to be honest. Obviously, yellow is urban area, orange is deeper water, purple is marshland. I forget exactly what green and red are defined as, but that's roughly what we have there. So these will turn into our labels for machine learning, right? We don't generally have ecosystem services, right? I don't have biodiversity scores for across Alachua County. I can't tell you at that location, this is 100% the biodiversity. But we do have lots of work that has gone into finding land cover for these regions. And I wouldn't say these are 100%, and I'll get into that caveat in a second. And then what we do is we're going to randomly sample points in the map, a lot of points. And we're going to use that as training data. So at each of these points, we're going to use the spectral statistics at that sample as our inputs into a model. We'll talk about the model in a second. And the output of that is going to be the land cover at that point. And the model that we're going to use, the machine learning model, is a random forest. So spectral statistics go into the random forest model. What comes out is our land cover label in training, or if we're doing testing, it's a land cover prediction. And we're using a random forest over, say, a neural network for a particular reason. So random forests are basically decision trees, but lots and lots and lots of decision trees. So you start at one point and you say, is this value here higher or lower than something? If it's higher, then we go over here. Then we look at a different feature, different spectral statistic. Is it higher or lower? Choose that, and it will go through the tree and make a decision based on all those different thresholds. And it has lots and lots of trees that all have different kind of decision points. And then it will take the average of all of those. The advantage of that is it comes with sort of a metric of certainty, right? Because I have basically an ensemble of these different machine learning algorithms that all give me these different predictions. If they all agree, then you can argue they are all pretty confident that this is what the land cover is. If a lot of them disagree, then you do not have confidence that this is what the land cover is. So what we're actually going to output for our land cover prediction is not the land cover. We're not going to produce a single class. We're not going to say this is clearly an urban area. We're going to output what the probability, according to this model, is of that land cover. And that's important because I'm trying to encourage my students and my collaborators to think, okay, this is not, right, if we're looking at an urban area is not just urban area. You know, if you look at urban areas in Gainesville versus New York City, clearly those are different environments. We may have more trees, for example. So there's a combination of other characteristics that should be taken into account, especially if you are trying to measure things like your ecosystem services. So we shouldn't just exist on these, you know, standard discrete classifications. So we look at these probabilities instead. Once we have these probabilities, then we can go into this ecosystem services matrix. So there are a number of ecosystem services matrices that exist which try to connect land cover with some score for ecosystem services. So high scores mean this area is good for ecosystem services, low scores mean they're poor for ecosystem services. So what we can get out is some weighted ecosystem services, one of those being biodiversity, for example. So what we can then do is we get out these weighted ecosystem services where we throw this in. So we throw in our land cover probabilities, and what we get out here, this is for biodiversity. is now a map of the entirety of Alachua County. And we're basically predicting this is what the biodiversity in this region should be. And you can see some trends here. You can see sort of on the right-hand side, Eastern Alachua County, where there are, I'll show this in a second, higher marshland areas, we see generally predictions of higher biodiversity. And this is, you can see here. So more wetlands in that region. So that generally connects with what we might expect. Whereas the other areas of Alachua County, they're not necessarily super low, but they have lower general areas. And we can see areas such as Gainesville have generally lower scores over here. And we can also obtain not just a single ecosystem service, but if you wanted, you could build a composite score of all possible ecosystem services. So if I summed all of these together, and I will note, I don't necessarily think that is probably the best approach if you wanted to characterize all ecosystem services, but this is going to be a simple example of one thing you can do. You can sum them all together, and high ecosystem services scores will mean this place is best for ecosystem services in general. Low ones will mean just this area is not very good. So we can do that for a more specific region, like Gainesville. So this is Gainesville. Again, this is University of Florida right here. This one's 13, Waller Road's right there, downtown is right here. So if we apply that, if we look at the land cover for Gainesville, it's pretty boring. Slightly different colors than we had before. So this is all urban area. Again, I don't remember what green is. We have water right there. But basically, the land cover map that we have is extraordinarily dull. And if you were to just base your ecosystem services on this land cover map, you really wouldn't get all that much information. If we look at some other scores, we can look at NDVI scores right here, which is often used for talking about plant health. High values give us high plant health in general. Low give us low. You can see that it highlights that there are more urban areas, buildings and all that give us low scores. Other areas give us high scores. If we take our algorithm and put this in there, we get this as a result. This is, again, using super pixels, so it's not quite as high resolution as we see in the NDVI, but we can see some nice clear trends that are kind of interesting. We can clearly see, again, downtown Gainesville and the university. We can see Waller Road and 13th right there. But one thing that's quite interesting, if you look at it, is this area here, which has kind of larger white values than other areas. Interestingly, if you nicely trace some river systems and elevated regions in Gainesville, this is where Hogtown Creek is. And this is, I would not claim this as a clear validation that this data is right. This is more observational. This seems to be giving us right answers. But we can see that the water tends to go down, right? These river areas, or go down into these river areas, the creek. And we seem to get higher ecosystem services due to that, or correlated with that, I should say. So we can see some very interesting patterns from just this, of which we don't really see that in the NDVI. Possibly a little bit if you started smoothing out, that might actually come out of this, but it's not quite as clear in this particular case. Another interesting example, this is a little bit more to the southwest in Alachua County. So this is just a picture of those areas. We also have this nice region where I believe there's a timber farm. So we have this region. If you look at the satellite imagery, it's clearly this area has no longer trees in it. We don't actually see this so much in the NDVI. So we have an area with less trees. Actually, sorry, this is the area where there's trees removed. So this is the area where we have like trees all in a line in a nice, clearly set area. Whereas over here, this is the more wild foresty area. So we see no difference over here with the NDVI. We can kind of see a little bit here where there are no forests or no trees, but we do see a huge difference here. Whereas in the middle here, this is where there's a small patch of trees that's still right there. So that's an interesting additional kind of comparison. So this is our general approach. We have not really published any clear validation of this because validation becomes kind of difficult. But the benefits of this approach is what we've been able to do is we've been able to take what I say is these weak labels, these land cover labels, and use that to our advantage of it's not just this is an urban area or a forested area. It is really some combination of both, and use that to make a nicer gradient of land use or land cover and these ecosystem services. This also means that I can train and test on the same data sets, which is usually a huge no-no in artificial intelligence and machine learning. You don't train and test on the same data sets, but you can sort of think of what we're doing instead as denoising data, right? I can train with the data and then say, the data's wrong. What should the real data be? And this easily in quotes, can easily scale to much larger regions as necessary. I say easily because still running this on all of Florida takes about a week on Hypergator. So easy from the implementation perspective, from the computational perspective, not so much. And so we've been working on building this toward scaling to the entirety of Florida. We have some preliminary results. This is a preliminary result for biodiversity. There are some areas, so you can see these weird gaps here where we are missing data, and that's more of an issue of just there's cloud cover during that period of time, and we don't get the data. There's some other issues that have to do more with dealing with different projections on the maps and all that that we're still fixing. But in general, you can see we can go across the entire state of Florida and build these kind of maps, which is very interesting. Again, one of the challenges is validation. This is actually in this slide. We're looking into good ways to do the validation now. If anyone has any ideas, I'd be very interested in listening to that. We're looking into soil properties right now because our collaborator, Dr. DeBow, has soil property measurements all across the state of Florida that we're trying to do correlation with. But there are other questions as well that we're looking to answer. Like how should we choose the training data? One interesting question is not all of Florida looks the same. So why should I be training on Northern Florida and using that for Southern Florida? The answer is probably you shouldn't. But how should you separate things? There are ecoregions that exist that the literature has come up with. Are those the right ecoregions? We don't know for sure. So can we come up with our own ecoregions that we should be using for this sort of training? Maybe. So we're looking into where should the training data come from for each testing area. And how should we design the machine learning architecture as well? We chose random forests for a particular reason, but there's still lots of hyperparameters to be chosen. And I like to have these chosen for particular reasons. We know why we're choosing our machine learning models in the way that we are. Not just, we're not just throwing machine learning models at things and saying, it works. And how you change the parameters does change the results you get to some degree. Kind of on one side goes closer to just giving us the land cover labels, and another side going closer to, just everything's the same value to some degree. So that's the knowledge route. The last route I want to talk about is the synthetic data route, where we have lots and lots of simulated data. So this is a research team of postdocs and graduate students of Rishab and Krishna and Pratik. Rishab's been working with Dr. Zotarelli and has been, he is really an expert on the DSSAT crop model that we are using and has been invaluable to this. Krishna and Pratik have been on the machine learning side, building the two models that we're going to be talking about. So the challenges here, we're interested in potato production, and specifically how do we give nitrogen recommendations for planting seasons. And as I said, I am not an IFAS person, so I'm going to just do terrible at explaining this, and most of you can probably do it better than me. So I'm going to probably just brush over it. But basically, this project is looking for doing soil nitrogen recommendation systems. But in order to do that, we need to understand how much nitrogen is in the soil at any given time. without measuring it. We can measure it, but it's difficult, and we can't do it all the time. Can we figure out what's going on in between all those times we do the measurements? So we want to know at any given time, what is the amount of soil nitrogen in the soil? Can we use crop models? There are crop models that exist. We're going to be using the DSSAT model in this case to help us out. But as I kind of stated, these simulation models are not quite correct in all cases. On top of that, they require a huge amount of calibration. They're almost kind of machine learning systems in their own right, because instead of having an algorithm that does it, you have a researcher there that sits there and calibrates, does all the tuning of all the parameters in order to get just the right prediction of the crop. So there's one that they're not generally not accurate. You may not have always the right parameters to choose, and then you still have to kind of calibrate it manually, which can take months of time to do well. Why not machine learning in general? This goes back to, we can't just use data for everything. So what we're trying to do is build crop models that are guided by machine learning. And basically the goal, as I said, is we want to be able to predict how much soil nitrogen there is at any given time. So if we have these measurements over here of nitrogen in the soil, and we have some simulation, we want to create some better prediction of what these should be. And I'll skip over some of this, partly because we're beginning to get close to time. But we're going to take two approaches. The first approach that we took was using an LSTM model. Won't go too much into it, but basically the idea is we have a DSSAT model here. So DSSAT will give us a prediction of how much soil nitrogen is in the ground, given all of these calibrations that we've given it, as well as a whole bunch of data, weather detail, soil data, when nitrogen was applied to the soil. And then we feed that data into a machine learning model, an LSTM in this case, that is good for dealing with time series data. And we'll incorporate some more information into the soil temperatures, what information, the growing days, moisture conditions, and build a model based on DSSAT. And so this is all now just a trying to replicate DSSAT more or less. And then we can add in observations of soil nitrogen saying, well, DSSAT's probably not quite right? We can try to mimic DSSAT. We can build a surrogate model for DSSAT, but it's not right. So we need to fine tune that with our own observations, which are very sparse. And from that, we can try to fill in all of the gaps. So this is what the actual soil nitrogen is at all these different times. And so these are some of the results that we get, where our observations are these black dots. Here's there we are. These black dots are all of our observations. These are different fields with different applications of nitrogen, which are shown here. And the red is what DSSAT proposes, and the green line is what we're proposing. And you can see they're not terribly that different, but you can see areas such as right here, where we're definitely doing better than the DSSAT model, right there and right there. And if you look at all of our observations versus the estimated, we're the green here with our hybrid model, and DSSAT is the red. So you can see that the DSSAT tends to consistently underestimate the soil nitrogen content, whereas we're much more a straight line close. And we provide 22% improvement over DSSAT. And that is with a calibrated DSSAT, I should mention. If you did a terrible calibration or whatnot, you can improve upon that more than that. I'm going to skip some of that. So what we're going to now from this is, can we do better models? So there's some small caveats with our previous model of that. We also needed DSSAT to be an input into the model. So we're trying to get rid of that. We're trying to build a pure surrogate of DSSAT, and we want to do that more accurate than we could with an LSTM. So we're looking at a transformer model to do that, and an XGBoost model to do that. And this will take all of, again, the DSSAT. In this case, before we did data from DSSAT that was very focused on the particular farms that we were looking at. In this case, we're just trying to get millions and millions and millions of DSSAT measurements and all put them into these machine learning models to basically try to mimic what DSSAT knows. And once we can mimic what DSSAT knows, we can just input all of our information into our new machine learning models and get out outputs for these. This is showing our data sets. So for predicting soil nitrogen with the transformer model, we're using up to 4.7 million DSSAT simulations with lots of different input features over 19 years of training, 4 years of testing or validation, depending how you look at that. We're also building models for nitrogen leaching and for the amount of tuber that gets produced. And I'll show these. In general, they're very good. So this is with any experimental data in this case. So the previous one was with experimental data. This is just demonstrating that we can replicate exactly what DSSAT's giving us with our machine learning models. So DSSAT is the red line here. Our transformer model is the green line. And we're pretty close. It's a little bit off in places, but we're able to fairly well predict what's going on. This is with nitrogen leaching, and this is with tuber growth. A little bit more off here on these ones. And then what we're going to do is similar to what we did in the previous case. We're going to take our field observations. We're going to use that to fine tune the model and actually try to figure out what nitrogen is in the soil at any given time. We're also looking at combining what we were talking about in the previous routes for AI with this. Can we utilize satellite imagery to now look at these areas, combine that with the DSSAT model and the data that we're collecting, and try to basically predict what is the soil nutrients based on the satellite imagery. So a lot of possible directions that we can go. And this will ultimately be used to build a nutrient recommendation system for potatoes. Still quite a bit of ways to go, but we've done quite a bit at this point. So that's overall everything that we've done. In general, we're trying to find ways to quantify ecosystem services. There are a lot of routes to go. There's a lot of research that could be done. And I think there's a lot of potential here for artificial intelligence. But from my perspective, somewhat biased perspective, I don't think we can just go sort of the traditional route of take lots and lots of data, shove lots and lots of data into a machine learning model, and we get out, our answers. If we want to especially do something at large scale, we need to incorporate additional information, knowledge of some kind, either knowledge that we've collected over many decades of research in these fields, or knowledge that we have from simulation engines or any kind of physics that we know. And that's what I've been trying to do. And ultimately, a lot of this work has been sponsored and supported by producers who are interested in this work. So we would like this to go back to them. And that's the entire presentation. Thank you very much.
Thank you, Joel, for a wonderful presentation. So we have about 10 minutes for questions. If anyone in the audience have questions, please unmute yourself and speak up.
Hey, Joe. Yeah, thank you very much for your nice presentation. Very nice work. So I have a couple of questions. The first one is regarding the satellite image land cover classification. You used the random forest. I remember I saw some papers recently. People are using this, ChatGPT or Vision Foundation models to classify those pixels, segment those pixels, and also can this GPT and this large foundation models can do reasoning of basically like using the knowledge, right, to reason whether this field is agriculture, what kind of crop field, agriculture field, or other ecosystem services, stuff like that. Have you considered that approach?
That's an interesting question. So actually using like LLMs and all that to do that sort of reasoning, haven't thought about that necessarily. And that might be because I'm a more quantitative person. I want the numbers and use the numbers for that. I and I'm sure many other people would be concerned a little bit about it not getting it right to some degree. But also I think, as I stated, we're using random forests for a particular reason of trying to get these probabilities out. So even if they were to say, oh, I think this is urban area, I don't think they would give us a quantifiable, this is an urban area 10% and forested area 90% or something like that. And you could do that potentially with neural networks in general, but actually it's not. There are issues with doing any kind of uncertainty quantification with neural networks. I have another student working on that. There are techniques, but they don't quite have the same kind of reliability in terms of interpretability as a random forest does. So I'm actually a little bit skeptical of going down that route. So that's basically why we're using a random forest in this case, the quantifiableness, or using quantifiable information versus an LM, and the ability to get these probabilities out.
Okay. So Joe, another question is, have you published papers related to these studies? I think those would be very useful if you can provide the references. We can read the papers.
We have one conference paper in IGARS on this work. We have one paper in computers and electronics and agriculture for the nitrogen recommendation work. And that is everything at the moment. But I can provide those. I'd be happy to do.
Yeah, that'd be great. Thanks. That's all from me.
Any other question for Joel?
Joel, this is Cam Hunt here in Tampa, Florida. Just curious if you've been requested or had opportunities to apply this kind of eco-service analysis to aquaculture or any of the coastal services.
We have not. We have some ties to aquaculture through some of our stakeholders, but we've not specifically presented this for that. That's almost kind of follow-up work. We're actually looking for new funding that's more along the lines of looking at water quality and water quantity, because we've done a lot of engagements with stakeholders. And in terms of ecosystem services, the thing that keeps coming back to us is that water is the most valuable thing in Florida right now, and we really need to be looking at water. So that is on our radar. And I know water kind of goes across both land and aquaculture, so it's not quite just aquaculture, but we do have connections with aquaculture. If you have particular interest in this, I'd be interested to talk about it and see what opportunities there are. Because again, I'm the AI side of this. I'm not the person who knows all of the agriculture or aquaculture stuff.
Totally understood. I will send you a follow-up note. Thank you.
Excellent.
Any other question for Joel? It sounds that there's no more questions. We have still a few minutes, but if there is no questions, so yeah, I thank you, Joel, for your presentation, and I thank everyone for attending to this seminar. It was a great presentation, and thank you very much.
Thank you all for coming. It was a pleasure to give this presentation.
Sure.
Thank you. Bye-bye.
Bye.
Thank you, everyone.